But if I do let you look, please return it. I think we're going to go through the mid-range example. It'll help us with a couple things. It'll help us with the joint order statistic. There's two order statistics involved in the range and the mid-range, but it's a transformation of those order statistics. So we'll get some transformation stuff. I'm going to give you a new homework on Monday, but you already know what it is. There'll be some transformation problems from chapter 5. Once we get through the delta method, I think what we'll do is switch the chapter and jump to chapter 6. And then what we're really doing is chapter 6 will be relatively, there's a couple things. Sufficiency is the big deal in chapter 6. Once we get into chapter 7, we'll spend a lot of time there. We have to cut all this together soon. Okay, so we're still kind of doing preliminaries. Let me show you one more probabilistic thing. This is the inverse CDF sampler. This is just a side. Inverse CDF sampling. Let me just give you an example first. I'll tell you what the algorithm is. I'll give you an example. This is the example I used to generate samples from, not this distribution, my distribution that I used to exemplify order statistics. So we'll look at this example. F of x is equal to x over 2. X lives between 0 and 2. So this is my simulator at the top of that piece of code that samples from this function. I think that's all online. So you can look at that. But I have just one little step where I generate a uniform, and for every uniform, what I get is a perfect sample from that distribution. I say perfect sample, I mean you just get a sample. There's no asymptotic thing. It's not I have to run it for a long time and get anything to converge. It happens right away. So there are types of samplers that are more flexible than this sampler and extend to more difficult cases, but you have to pay a price. So you have to wait for a while for things to converge. Like Newton's method, like a lot of iterative matrix solves, you have to wait for a while. And there's some certain guarantees that you can have and things that you look for to make sure everything's converged. I'll probably say something about those algorithms later on. Here's how the inverse CDF sampler works. So just in general, the algo looks like this. You compute the CDF. So I'm going to integrate dx between whatever its left bound point is. So I usually just denote that by negative infinity and make sure that you've got some indicator to zero things out if we've exceeded the bounds of support. And I love to overflow my notation. That x is not that x is that x. So be careful with that. I think the thing that people like to do is maybe make this an x tilde, and I'll let this go to c goes to x. So my calculus TA back in college used to convince me this was the correct way to write things. And that's fine. I still did this. Because everybody else does. Just keep in mind, this is slightly different. This is a dummy variable right here, and this is that element. I think we all know. Okay, so that's the CDF. What we need to be able to do is invert this. So that's the inverse part of everything. So I love the algorithm's name because it tells us exactly what it is. Invert to get F inverse, x. I'll make it a function of the exact same thing. And then what we end up doing is we generate a uniform. Zero, one. Keep in mind, CDFs are defined on the support, like the inverse CDF is defined on 0, 1. So the CDF is a map from something to 0, 1. So the inverse is a function of 0, 1. So what we're going to do is we're going to take our sample, from our uniform, and we're going to generate a sample right here. Now I've overloaded x too many times, so I'm just going to call that xi. I'm going to call this ui and this ui. So you generate a new uniform every single time you plug it into that function. You get an x out of it, and this x is distributed according to this density. So let's prove it. So that's the basic idea. Let's just do the example first. So our example is just integral x over 2 dx. This is f of x. This is going to be up my exponent by 1, divide by my new exponent, 4. Is this right? That's my CDF, the inverse CDF. So this isn't too hard to do. This is how I always do it, is I end up just taking x squared divided by 4. So this is the inverse. I set it equal to something. It can be any dummy argument, and I'm going to change the name of that argument later on to x so that I'm on the same page with what I've done before, but I'm using x entirely differently. So we'll just call this z, something like that. So I'm just going to solve for x. X is equal to the square root of 4 times a z, right there. So this is my inverse function, but now I'm going to change the name of it. That's my inverse function defined in terms of z. So now I'm going to use the notation one more time and just call that thing x. So this is f inverse. So f inverse x, when I change the argument name, it's just this, 4x. So that's the inverse function. So set it equal to something, solve for it. Why don't I need the negative side of all of this? Because everything is positive. So this is all I did. So I took a uniform, I plugged it in right here, and it transformed it in just the right way. And it gave me samples from this other thing. Let me just hear real quickly, what are limitations to inverse CDF sampling? Why can't we just do that all the time? It's awesome.
We don't have an inverse.
If you don't have an inverse to the CDF, is one reason you can't write it down.
You don't know the CDF.
You can't write it down, yeah, analytically. What's a good example of a distribution where you can't write down the CDF?
No.
Normal's perfect. So cap phi, that thing, is it's something, it exists, but you can't write it down. So people don't use this sampler for sampling normals. I would agree you could build up like a step function for the CDF, and you could come up with an approximation of all of that and try to invert computationally the CDF. Don't do it. It's just kind of, there's always a better sampler than that. But in spirit, it's fun to think about. David?
What do the art people do?
Fox-Mueller. So for 2 uniforms, I can give you 2 normals perfectly.
They also have, I think, an inverse CDF function.
But not for normal. So that's would not be the right way to do it. So, but Fox-Mueller is the famous algorithm. There's a whole bunch of variants of that algorithm. It's one of these polar coordinate sort of things that you have to kind of think about. Normals have a lot to do with that. I can write down what that transformation is later for you, but it's some sines and cosines, trigonometric stuff, some logarithms that you take. But that's how R will do it. For an exponential distribution, R will do inverse CDF because that one's easy to invert. So super fast. Okay. So let's just prove that this works. Proof for inverse CDF. So what I'm going to do is I'm going to define some random variable. I'm going to talk about the inverse function of x right there, and I'm just going to call it something else. I'm going to call it y. Okay, so that's a transformation of everything. So, uniform, I'm going to call that one. So that's what we actually plug into that. So it's a transformation of the uniform. Gives you something else. So I transform, I apply a function to a random variable, I get something else back, some other random variable. So I want to know what is the probability distribution of y. I'll call this little y right here. So I want to know what this thing is, the probability distribution of that. So that's this. If I were being polite, I'd probably make the random space cap u or something like that to describe the process of generating uniforms. So I'll just plug this thing in. Probability distribution of F inverse U less than 1. I've already inverted the function, so I assume that it's invertible, so I can go the other direction. So again, if you can't invert the function, this is out. Can't use it. Since we've already inverted it, we've assumed it's invertible. This is probability distribution of a uniform. I'll try to be consistent. Is less than or equal to F y. So proof's almost done. There's only one more thing I need to say. So let me just ask you a basic question. What's the probability that a uniform 0, 1 is less than 0.75? 0.75. What's the probability that a uniform 0, 1 is less than 0.23? 0.23. What's the probability that a uniform is less than smiley face? Smiley face. So whatever I call this thing, the probability of the uniform, less than that is this. So this is by CDF. So that is the CDF function. So what's the probability distribution of y? It's the CDF for the random variable y. So they have the same probability distribution, so it's the same thing. That's the proof. Try to remember that. This is kind of the what I would call a shallow proof for understanding why a p-value is uniformly distributed under the null hypothesis. And if it's not the null hypothesis, it's distributed differently. That's what I consider the full-blown proof, is understanding how a p-value is distributed when the null is not true. We'll come to that in chapter 8. So there's an algorithm for you. If you want to create simulation studies, this is an easy trick. Okay, review of joint order statistics. Let's come back to this. This is where we left off last time. Let's just draw the exact same picture. So I want to know the distribution of xi. And I'm going to say I is less than j, and these values are bounded by each other. So this is the ith largest thing. This is the jth largest. I's are allowed in all of this. Doesn't change anything. Then draw my picture so I can remember what this density function looks like. If we're dealing with joint distributions, write down the density. Don't try to write down the CDF, because that's not a convention we agree on, which way to add things up in 2 dimensions. 1 dimension is just ordered for us automatically. That's what is so elusive about high dimensions. It's not ordered. So we don't know what's big, we don't know what's small. It's hard to say. Okay, so here's my illustration. If I were going to come up with a formal proof, I would still draw this picture and look at it. And then I would kind of talk about these density functions as probabilities and build little tiny intervals and then collapse the interval and take limits. If you want to call this a proof and just look at the picture and write down the formula, I'll accept that. So I think to a physicist and an engineer, that might be a substitute for a proof. A proof is just a formalization of that idea. So I like the illustration, to tell you the truth. I couldn't ever understand it when I was tutoring real analysis in college. And they would say, my professor told me I can't use pictures. And it's like, they can't stop you. So every time I build a proof, there's a picture that goes with it. I think they just want to make things too hard to exclude a whole bunch of people. So I'm not sure what's going on there. So I'm going to call this the ith largest. I'm going to call this the jth largest. I'm going to give these some names on the real number line. I'm going to call it U and V. I probably could have called it Xi and Xj, but I'm just going to pick something different. This is what they do in the book. So again, these are just dummy arguments. So if this is the ith largest, I know that there's I minus 1 things over here, and I can permute these around in I minus 1 factorial different ways, and it's indistinguishable to me. What we're permuting when we think about that is the labels on the IID replicates, who don't care which way they fell. So even though this is continuous, I still think about dice rolling, and I'm thinking about this continuous dice that I'm rolling. It doesn't really exist, but I can still imagine it that way. And so I don't care which order the dice fall on these numbers, I just care that they do, and I want to count up the number of ways that that can happen. So this is the jth largest, so that means there's n minus j things over here with n minus j factorial different reorderings for the exact same reason. And the number of points in here is going to be j minus I minus 1 factorial. Sometimes I like to think about this as j minus 1. That's all the number of things here, because that's the j things, so I've subtracted that out. And then I want to just subtract off that, all the I things in here. So if you want to write that down to j minus 1 minus I, maybe that's how you thought about it. All the same stuff. Then I just need to come up with the probabilities of landing in these different areas. So this is going to happen with probability f of x, u. This is going to have probability of being in this region of f of x, v minus f of x, u. And this is going to be 1 minus f of x, v. Now I'll say this just a little bit wrong. The probability of being at this point right here is little f of x, u. It's not a probability. If I built a little tiny interval around there, I could call it a probability, but when I collapse that down to a point, we get the density function back. So not a probability, but it kind of acts and feels very similarly. And this right here is f of x, v. So now I'm just going to stare at my picture, and I'm going to build up this probability density. So f of x I, xj. I'll try to be polite and tell us what those actual random variables are, and give it some descriptor that I can remember what it is. In the first place, I like notation because it reminds me what I'm doing. U and V are going to be our arguments. This thing is just going to be the total number of ways that I can reorder all of these points, and then there's some things that I want to distinguish and pull out those orders that it's basically just repeats of the same thing. So n factorial different reorderings, some reorderings that I don't care about, so I'm going to remove those. I minus 1 factorial, j minus I minus 1 factorial, n minus j factorial. If you'd like to put in the 1 factorial and the 1 factorial into there so it all adds up, probably do that mentally, but if you write it down that way, that's fine too. So we just know that that's 1. And I just product all these things up. F of x, u. I've got this raised to the I minus 1. That's the number of things that are in that first region. I want to account for that density function, f of x, u. Now I'm going to do the interval in the middle. It's f of x, v minus f of x, u. Raised to the j minus I minus 1. And I've got the other density, f of x, v. And I've got the last interval. It's f of x. That's 1 minus f of x, fx of v. I'll raise that to the number of things that are in that interval. So I'm just using basic probability rules to build this up. I want this to happen. I want that 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 to happen. So when I say and, I'm thinking multiplication. So that's our formula. Could you do this for 4-order statistics if I gave them to you?
Yeah.
Just draw a picture. So same idea, it just extends. So really, I've just shown you grad school level induction. With this, you could extend it to any case without actually doing the induction move. So I like it like this. If you like it more mathematical, that's fine too. So there's plenty of places on the internet where you can see more complicated derivations of this. They really are the same thing in my mind. Okay, so let's use this, utilize this, and talk about the range mid-range example. But what we need for the range and the mid-range is we need to look at the joint distribution of the max, the min, and then I need to transform into the range and the mid-range. So, example. Find joint of the range xn minus x1, the minimum, in the mid-range. It's going to be the average of the max and the min. It's a weird statistic. If I saw anybody actually using that statistic, I would probably correct about it. But it does make fun probability problems for us to study. So joint for x1, xn. I'm going to call this f of x1, xn. And I'll be a little bit polite down in this notation. Don't expect everybody to be that polite for you and tell you what those things are and try to be consistent. Now I'm going to be a little bit less polite, and I'm just going to call this x1 and xn, because I like to think about what they mean instead of just writing down u and v. I need a placeholder to remind me what the significance of those two things are. So I'll just write it down like that. So again, we're going to be looking at xi's coming from a uniform distribution on 0 theta. So this will be our example that we're using. This is where we started off. So just as a reminder, f of x is 1 over theta, and cap f is x over theta. And I'll try to continue to be polite. Just write the x's down there. So that's the CDF, that's the density function. We're going to use both of them to build up this joint distribution. Let me just ask a quick question. It should be obvious conceptually, but even more obvious if you're just staring at this equation. Is the ith order statistic independent of the jth order statistic? I thought everything was IID. You've ordered everything. So you've built in dependence on everything. So no, you have to know what all the everything was to reorder it. If you don't like that, you can stare at this equation right here and see that you can't factorize a part of this. You can factorize that stuff, but you can't factorize that. So no matter how hard you try. So we know that they're not independent, but conceptually we know that too. Okay. So we just plug everything into our formula. So this is going to be n factorial. I'm going to look for I is equal to 1. So just using our formula, I is 1 and j equal to n. So if I just substitute everything in. So I've got I minus 1, that's just 1 minus 1, factorial. I've got j minus I minus 1, so that's n minus 1 minus 1, factorial. Another way of writing that is n minus 2 factorial. And then I have n minus n factorial over here. So a lot of things that are just 1, 0 factorial is 1. So that's at least this part. And then I'm going to multiply it by everything else. So times, we'll simplify that later. My two different densities, I'm just going to plot those, I'm just going to write those down first. So I'm just going to do this a little bit out of order, but I'm just going to write down this is 1 over theta squared. So those are my density functions. Then I've got this probability. This is going to be x over, I'm going to call it x1 over theta raised to the 1 minus 1. So that goes away, but I'll write it down anyway. I've got xn over theta minus x1 over theta. This is going to be n minus 1 minus 1. I'll just speed things up and call that n minus 2. And then I've got this other thing that goes away as well. So this is going to be f, do this, f of x, f of xn raised to the n over n minus n. This is just xn over theta. So again, we're just copying from this. Not doing too much thinking as we do it. So we thought about that for a long time, now we're just plugging things into the equation. You do it enough time, you'll get swift. I still write down the full-blown equation every time I do this sort of thing and just plug into it. So that's equal to n factorial over n minus 2 factorial. We could simplify that if we want. If I were coding this on a computer, I probably wouldn't compute n factorial divided by n minus 2 factorial. I'd probably look at n times n minus 1. And that's what I would code up. So you try to do that with extraordinarily large n, it's going to blow up on the computer. Quick question. How big of n could I plug into a computer and compute its factorial and be confident that the number it gave me is reasonable? Maybe a little higher. Higher than that, even when I was in college. So
50 or so?
Yeah, it's about 50. So, but we're in the same order, right? So it's like 52 will break double precision. So you need something more. So maybe, who knows, computers these days, maybe we could get like 60 factorial. Say what?
It depends on how, or I think there are ways you can go about it and get the high factorials fairly accurately.
I see. There's approximations that you want to use. Sterling's approximation, things like that. So that's true. So there's tricks that people can do. Okay, so we'll just continue writing this down. So this is just 1. This is just 1 right here. So I'm going to remove all of my thetas. So I have 2 thetas down here, but I have n minus 2 thetas that I can factorize out of this. So I'll just write this down as 1 over theta to the n, xn minus x1. Put that 2 over here. To the n minus 2. And I think that's it. I have to be a little bit polite about this and remind us that these things are ordered. So x1 is less than xn. Those are bounds of support. I need to be even more polite and tell us where these are bounded. So those are my constraints. And that's the joint distribution of the max and the min. Everybody good with that? Cool. When you guys get super quiet, I get worried that I just wrote something wrong. I feel confident. Cool. Let's transform. we will move to the range xn minus x1. I'm just gonna abuse the notation a little bit because these are my dummy arguments that I've been using. If you want to do this, that's fine. I make you more comfortable. So in mid-range, xn plus x1 over 2. First step in a transformation problem that I usually work on is just the inverse function of all of this. So let's do that. So I'm just going to change this around. I'm going to solve for xn and x1. So I already know this is invertible. These are just linear equations, and I can invert those. So let's just rewrite this. This is 2n is equal to xn plus x1. And I have range is equal to xn minus x1. I'm just going to add these together. So basically just some linear algebra in this, guys. So I add these two things together, I come up with r plus 2m is equal to 2xn. And so I can solve for that at xn is equal to m plus r over 2. So I did just a little bit of rearrangement here. So I can do the same sort of thing and subtract them from each other and solve for x1 itself. And it turns out it's this. So similarly, if I subtract the equations from each other and solve for the other thing, this is going to be x1. This is going to be the mid-range minus r over 2. Kind of makes sense. So it's smaller. We also need to solve for some constraints in all of this and understand how these two different things operate. So let me just draw a picture. Let's n factorial over n minus 2 factorial. I'm going to put this in a box so that we don't erase it. So I'm going to write it down like this. R, this is the range, this is the mid-range. Right here, the range we know lives between 0 and theta, and so does the mid-range. So it lives between that as well. So if I had two maximums that I got, which is unlikely, but it could, I guess, it's impossible. But we can use our imagination. So two mid-range, two maximums that I would get, I take the average, I still get the maximum. So that's theta. Similarly, the minimum, if I saw that twice, 0 and 0, then the mid-range would be 0. You'd never really see that. But it's at least part of the space. I like to do this a couple different ways. So I'd like to first just think about the endpoints of my distribution. Again, if I didn't know anything and I was really confused and this is high D, I'd probably start simulating stuff just to make sure I have the boundaries right. But I look at the endpoints of this. So if the range was theta, what would have to happen is I got the maximum point and I got the minimum point. And so that can only happen in one way. So that's the way I like to think about it. So there's only one way that can happen. If I had R is theta, then what would the mid-range be? There's a dependence. There's only one way I can get that range to be the whole interval. And so if I think about that, then I think about what the mid-range is going to be. I average the max to the minimum, and I get the midpoint. That's right here. So then I just start thinking about what these equations are. So if I were taking a test, I'd go, these are linear equations. Somehow, this point, and this point all connect to each other. So, and I would just draw a line. Then I would start verifying whether or not this was the right thing. This is the way I used to do it in calculus. I just check the endpoints. I'd think real quickly how to connect those endpoints. And then I might check a point here, and I might check some points over here and see if they adhere to the constraints. Let's think about it just a little bit differently. So I look at the equations, notes, linear equations, think about the endpoints, the most extreme stuff, and just connect it, and I'm done. So if we want to verify things just a little bit more, I can rewrite these equations right here. So this is going to be the mid-range is going to be equal to, excuse me, xn minus r over 2. And the mid-range is going to be x1 plus r over 2. So when I would start thinking about these things, what the bounds on these two things are. I have two different representations in terms of n. They're both straight lines. They describe all of the straight lines in here that I can form. What's going on there? So I want to think about the most extreme value. So this is maximized at alpha, so bounded above. My alpha is my theta. I think the book uses alpha. So bounded above by theta. And this one is bounded below by 0. So I'm just pushing those things out and thinking about the dependence, keeping the same structure so I can understand how the dependence effects are right here. So this right here tells us that n is less than or equal to theta minus r over 2. That's this line right here. And it's bounded below by 0 plus r over 2. So again, you just kind of write down everything in terms of one of the variables. I kind of like writing it this way. It's a little bit easier than doing it the other way. So you always have to figure out which way is easier to do. So that's everything that we have. And this is what we simulated at the beginning of class. So we created this triangular structure, and we saw all these points in here. So if I simulate, all the points live in those bounds. We've seen that already. I probably will not ask you to do some tricky problem where you have to think about the bounds of the space. That's probably the hardest part of any transformation problem. It's always nice when it still lives in a rectangle or something like that. So I'm not going to ask you anything like that on a midterm. So I can imagine everybody panicking and trying to remember what they did back when they were freshmen, where they could do this all a lot better than you can do now, probably. That's at least my experience. Okay, so I've got this bound right here. And I've also got that R lives between 0 and theta. So now I just need to transform everything. So I look into this equation, and I plug, anytime I see an xn in there, I just substitute this. Anytime I see an x1, I substitute that. But that's not it. It's not just plug it in chug. This is a continuous space, and we warp the space. We have to account for that warping. So to do that, I need the Jacobian. This is the absolute value, which is nice because I don't have to have any constraints on the way I order my Jacobian. So I'm just going to take my partial derivatives, pile them in there, and then take a determinant of that thing. So and that tells us how the space is stretched. So when I learned about determinants for the first time, and I've seen this in at least 3 calculus books, because I got 3. So when I was in college, so I could see different ways of explaining things. Lo and behold, you find your professor's test questions in it. So they have other books too. So other books are good to have. First time I learned about determinants and all of this stuff, they were telling me that the determinants of some vector space is the area of that space. So you can try to recall that too. So this is gauging how we've stretched the area through our change. So I'm just going to write this down. This is going to be dx1. I'll say dm dx1, I'll say dr. So that was perfectly arbitrary, but as soon as I pick that order of differentiation, I have to follow that order all the way through. So my other variable is dxn. dn, I can't put the dr there because I've already picked the n there. So dxn dr. I could have taken this and put it up here. I could have taken that and put it down here. And what would happen is I would have two changes of the negative sign and it would actually be the exact same thing. That's my Jacobian. Now I just need to fill it in. So I just need to take these derivatives. Derivative of x1 with respect to m. I try to remember this has to be a function of r and m. It turns out you could do the derivatives in the other order. M with respect to x1 and m with respect to xn. You could take the derivatives that way, find the Jacobian, but you would need to invert that Jacobian and then resubstitute everything in later. Turns out they're equivalent. So using those different tricks can make a problem pretty speedy in a midterm. I don't really care how you do it, just as long as you know how to do it. You know you can do all these other techniques. So dx1 dm, what's that? It's an easy derivative. So I'm taking the derivative of this equation with respect to m. 1. We can do that. So let's go for r, derivative of r. What's this entry? Minus 1/2. What's this one? This is m with respect to m. 1. And then this one? 1. So this is going to be 1/2 minus negative 1/2. I'll take the absolute value, although we got lucky. It just happened to turn out positive. This thing is 1. If you would have forgotten this, you would have gotten the right answer. But if you did this on a midterm or something like this and you didn't even attempt to talk about the Jacobian, I think you made a mistake and I'd mark you off for it. So even if your Jacobians are 1, make sure you derive that. Okay, so it really is just plug and chug. So I'm going to come up with this new equation. I'm just going to say FR, M. I'll call this R and M. Does that make sense to me? It's just f of x1, xn, x1, but I'm going to just change the equation to this is going to be a function of R and M. So I'm going to call this the inverse function 1, and then I have this other thing, xn, and every time I see that, I'm going to plug in its inverse in terms of R and M. Let me make that little r, little m. Times my Jacobian. Let me just ask you a question real quickly. For discrete spaces, do we need a Jacobian for transforming a probability model? No. So there's no stretch to the space that you need to account for. So it's just plug and chug. Only in continuous problems do you need the Jacobian. So we already know this thing is 1. That's convenient. And so I just plug everything into this density function. This is n factorial over n minus 2 factorial. This is going to be xn minus x1, n minus 2. But I'm going to substitute in my definitions for xn in x1. So this is going to be m plus r over 2 minus m minus r over 2. So the m's cancel in this equation. So this is n factorial over n minus 2 factorial. Then I can rewrite this. R minus 2 minus a negative r over 2 is 2 r minus 2's added together. So that's just r.
Are you missing the 1 over theta?
I am, yeah. So 1 over theta. That's right back here. This thing right here, I've been very impolite by changing my cap r's and my lowercase r's, because I said that's little m, r, and that's because I chose that one here. So this is just r. And there's something interesting about that equation. You don't see any m's in there. Probably make that a little bigger. So this is n factorial over n minus 2 factorial, 1 over theta to the n, r to the n minus 2. That thing. And I need to tell the dependence. So certainly n is in this equation, but it has something to do with the boundary of the problem. So r lives between 0 and theta, and m lives between r over 2, theta minus r over 2. Those are those lines. So there's our new density function. The book takes this a little bit further, and they do some integration, and they marginalize out r and m. Obviously, doing the integration in one direction is easier to do than the other direction. So when you're integrating over in this direction, you're just integrating between those lines right here. But going the other direction is a little bit harder. So I would have a look at those if you'd like to look at those margins, and they tell you a little bit more about beta distributions. One of these margins is a rescaled beta distribution. So where I take an interval between 0 and 1, and I expand it between 0 and theta. So if you want some familiarity and exposure to betas, you can read that, the remainder of this example. We have 1 more minute. I'm pretty sure we can cram in Taylor expansions and moment generating functions, right? Probably not. So just as a preliminary, what I'd like you to do is just study over the weekend, if you can, what Taylor's theorem says and what moment generating functions are. So a moment generating function, usually we write it down like that. That's the random variable. Here's a dummy argument that I take derivatives over. And this is just the expectation of xt. This is just the integral of ext with respect to f of x. By iterating over derivatives and solving t at 0, you get back moments. So we'll review that next time. We'll also review Taylor's theorem. Somebody real quickly, tell me what Taylor's theorem is. I'll tell you what a Taylor approximation is. So Taylor approx. I'll do this more generally next time. And I'll talk about the centering argument. I'm going to center everything at 0. I still call it Taylor, even though my calc books call it Maclaurin. So, but this is just going to be an approximation where I have k goes from 0 to some finite number. And I've got some coefficients in here. The coefficients are going to be kth derivatives. That's the kth derivative evaluated at something. We'll talk a little bit more about the significance of where you center all of this. This is over k factorial, and this is x to the k. So it's just a polynomial representation of everything. So go back and review that and make sure you understand where these coefficients come from. And I'll give you a 5-minute primer on this before we jump into everything. So we'll settle down and build it up from what we learned in calc class. But let me just see where you guys are at. What is Taylor's theorem? It's in all my calc books, so I know it's in all of yours. What's the actual theorem? What did you have to do when you did this in calculus class? I know this is a long time ago, but you had to do something. You could not just write down the approximation and you'd be done. You had to do this extra work to get full credit.
You have to take the function, take its derivatives, and use those derivatives as part of this function.
That's what I did right there. What's Taylor's theorem? What's the theorem? So yeah, that's how you use it. That's what you do, take derivatives of this function. So we need to know that the function is smooth, all of those things. So this is true when the derivatives exist. That's kind of built in. If you can't compute the derivatives and they're infinity, they're useless to you, something like that. But what does Taylor's theorem say? What's the actual theory part? Obviously, you can't just write a paper and say, here's what I did. Boom. That's what you say to your advisors. I did it, it works. Not good enough for me. You need to explain why, and I need some guarantees.
Is this something that the radius of convergence?
Has something to do with the radius of convergence, so you needed to check that. So what is the radius of convergence all about? Yeah, so what it means is I can get rid of the remainder. So it tells me things about the remainder, and I haven't written down the remainder here. So it's comments about the remainder when it's negligible and we can throw it away. Also, Taylor's theorem tells us that the bulk of the function is approximated by the lower order terms. And so if I keep adding in terms, I get a better and better refinement to everything, but I don't see this big jump in the improvement. I see little refinements. So it's not like the first terms have just a little bit of the approximation, but I have to go down 100 terms to find, the big approximator. The terms themselves are ordered in how well they approximate the function. And there's a diminishing return. So that's kind of the nice part. So all I have to do to understand this function, how well it approximates, is look at the next term in the sequence, and that bounds the approximation. That's what Taylor's theorem says. The book is a little heftier about this, and they do slide all that stuff in, and they talk about it. So I want you to read through that in the context of the central limit theorem. We're going to see this twice. So if you think I'm just going to skip this one, it keeps coming up. So the delta method that we'll jump into right afterwards uses both of these preliminaries. So I'd like you to know about them. If you're an engineer in the class and you write down on a midterm or a final stuff and you just kind of say the remainder goes to 0, you don't say why, I'm going to mark you off very lightly. But if you do that on a qualifying exam, that's where you get in trouble. So I'm going to give you 2 different levels that you can say, I understand it good enough to get an A in the class, but I want to distinguish that from doing well on the QE, which are 2 different things. So I'll kind of talk about Taylor's light, and then I'll talk about Taylor's heavy a little bit more, and tell you what you need to do with that remainder. But I want you to pay attention to the remainder term in their argument in the book, and we'll reconstruct that next time. That's it, you guys. Have a great weekend. Homework is due on Monday. So people have asked me, how do I turn it in? You're just gonna fill the stack right here. So I want your physical copies of the homework. I hate printing out homework. I hate sitting there printing them all out. I hate grading electronically. I like to sit down with the grader with a stack of papers and grade them, and we hand you back physical ones. So old school around here. You want to give it to me now? I can take it. Thank you. Oh, unstable too. Thank you. I'll leave it stable for you. Do you have a stapler? Mike, you got a stapler for us? Very good. You're the good community citizen. So I'll do it. I'll do it.
Well, I just have,
Look at you. Oh, look at you. That's a magic trick.